Hi everyone, this is Kona, and I'm just going to go over a little bit about multiple linear regression, just so you kind of have some working information, knowledge, but then you'll really want to look at the other video where I work through the mini-tab, because that's where we really dig into what this means and what we're doing. So multiple linear regression is one response or y variable and more than one predictor explanatory variable. It just builds on the simple linear regression that we've done by adding on additional predictor or x variables. What we want to know is if any of the predictor x variables are significantly correlated with the response variable, but this is the big part, taking into account the various correlations that may exist between the predictor variables. So this is actually, it's not just doing a bunch of just simple linear regressions, it really does take into account the different correlations that may exist between everything. So it can tell us if variables are related, cannot help with causality, so please don't say something caused something else. The assumptions required are just the same as those required for the simple linear regression, except they must be true for all the predictors. So the equation is really similar to the simple linear. You've got your y hat, the response, which is your predicted value of y for given x values, the y-intercept, where the line of best fit crosses the y-axis. You've got your slope k. Slope k is just here, it's like that slope 1, slope 2. So k is just the numbers for however many variables you have, and it's just the slope associated with whatever variable. It's also known as the coefficient of the variable. And then xk is just the x value for the k variable. So there's your equation. Inferences about the parameters. You've got, first of all, t-tests for the slope coefficients. And that analyzes the significant predictive value that a variable adds to the model when the other variables are already included in the model. Values of the slopes, and that's interpreted as how much of a unit change in y will occur for a unit increase in a particular x predictor variable, given that the other variables are held constant. The coefficient of determination, or the r-squared adjusted, so this is important, we're not just using r-squared, but we are using the r-squared adjusted this time, measure the amount of variability in the response variable y that is explained by all of the predictor variables in the model. And then we have the Anova F-Test, which is test whether the equation as a whole is statistically significant in explaining why. So here are the different values or things that we'll be looking at when we actually start doing it in mini-tab. So significance testing, we want to know whether a particular x variable is making a useful contribution to the model. We're testing whether the slope of an x variable is equal to 0 or null, or not equal to 0, the alternative. If the slope is equal to 0, then that means the variables are not related. So if slope is equal to 0, the variables are not related, so it's not of any interest to us. So the null hypothesis, the response variable is not affected by predictor variable 1, 2, 3, and so forth. Alternative hypothesis is the response variable is affected by predictor variable 1, 2, 3, and so forth. What's the purpose of this analysis? Basically, we're trying to figure out which evidence or data provides the strongest case. Or more specifically, we just want to know whether a particular x variable is making a useful contribution to the model. That is, given the presence of other x variables in the model, does a particular x variable help us predict or explain the y variable? And why is this important? Well, here we go. Our recent election. So obviously, the regression models for the election this year, for Trump versus Clinton, didn't really, this past year, didn't really work that well, right? Well, part of the problem is that you've got lots of different x variables that they've probably factored into their regression equation, and you need to know if you have too many, that's a bad thing. So you want the fewest number of x variables that will give you the best prediction of your y variable. And so in this, it's kind of a give and take in that you don't want too many x variables. So you don't want 10 x variables, but you do want to explain a lot of the variability. You want to be able to explain why. And so it's kind of this give and take to try to figure out which variables make the best response. So next up, watch the mini-tab video and we'll actually dig into this.